Okay, so here we go with lesson 11.2. You should have completed problems 1 through 7 to start with. So I'm going to begin with number 8. And if you read about Gauss's story, he was very clever, we believe. We think this is how he did it. Instead of just adding them left to right, he added numbers 1 plus 500, 2 plus 499, 3 plus 498, something like that. Because if you pair up your numbers that way, then every sum is going to be 501. And if you're pairing them up, then you'll have exactly half as many pairs as you do numbers. So if you have 500 numbers, that would be 250 pairs. And that is a much easier calculation for finding the sum than to add them up left to right. Much quicker too. So this is the formula that we actually use then. If that is in fact how he did that calculation, what he did, of course, is, if you want to write it in a formula form, he took the first term, a sub 1, plus the last term, a sub n, and he multiplied that times half as many terms as you have. In other words, if there's 500 numbers, there'll be half of that pairs, and these pairs all add up to whatever the first and last term adds up to. So that would be one way to get the final answer that he got. So let's take this now to the next level. If we go back and remember how you find the nth term of an arithmetic sequence, this is from a previous lesson, lesson 11.1, we learned that as long as you have at least one term, the sum formula is the first term plus n minus 1 times the difference. That's the formula we've already been using for a few days. And just as far as the definitions go, a sub 1 is generally the notation for the first term, and d is the letter we use for the common difference between consecutive terms in an arithmetic sequence. So if that's true, if that's how you find the nth term, then we can make another formula. In other words, the formula we just came up with, which we believe came from Gauss as a child, is to take half the number of terms times the sum. Well, let me write this up here. Gauss's term, let me write it as Gauss's. So Gauss's formula for the sum of a series would be, arithmetic series, would be 1/2 the number of terms times the sum of the first and last term. So that's Gauss's formula. But of course, that's great as long as you've got, if you know how many terms you have, and you know the first term, and you know the last term. But it is possible that maybe you would not know the last term. Maybe you just know the beginning, and you know how many terms there's going to be. You just know the beginning, but you don't know the end. Maybe it's so big or so long that you don't really know the last term. So if you don't know the last term, but we know the formula, because we did that back here, we know the formula for the last term, then we could come up with a whole different formula for finding the sum of a series. And what we're going to do is we're going to take Gauss's formula, but we're going to substitute for that last term a sub n and simplify, do some arithmetic and some algebra, and we end up with this formula. This is a formula that is really just a version of Gauss's formula, but what we have done is we've substituted in the formula for the nth term instead of a sub n, and then we did a little simplifying in here. So this is now the formula we would use to find the sum of an arithmetic series if we don't happen to know the last term. So it's a more complicated formula, but that's of course because we have less information. So let's take this formula and use it in a problem. So let's say there's a sum, and it's an arithmetic series. We know the first term, we know the difference, and we know there are 100 terms. 100 then would be our n. First term is 1, that's our a sub 1, and we know the common difference is 1. Well, those are the three things that we need for our formula. We need n, we need a sub 1, and we need d. So we can just find the sum of this by plugging in the numbers that we do have. So it's going to be 1/2 of the number of terms, which is 100, times 2 times the first term, plus n minus 1 times the common difference. So now we just need to take out a calculator and calculate the sums and products and all of those, and you get 5,050. So this is just an example of how you would use this longer formula if you did not know the last term. Now we turn our attention to a symbol that you have seen before. It's the Greek symbol, kind of looks like an E, but it actually is pronounced sigma. I'm sure you remember that from Algebra 2. That's called sigma, and it indicates addition. And it's actually a Greek capital letter for the letter that we might use in English as S, which stands for sum. So that's really the reminder that we're supposed to have is sigma really is S, and S stands for sum. So it's a shorthand way of writing summations, of writing series. It just helps us condense a lot of information into a short space. So there's different components. So let's start with this thing right here. And the way it's written here is A sub I. And all that really means is it's going to be some formula. There'll be some formula sitting there, and that's a formula for the nth term. That would be one way to describe that. That'll be the formula that generates the nth term. The nth term meaning basically any term. That's the formula that'll generate the first term, the second term, the third term, the fourth term, and even the last term. That's the formula that generates any term in this particular series. So it's going to generate the first term, it's going to generate the second term, it'll generate the third term, and it'll even generate the last term. So there'll be some formula here, and using the subscript in this particular case, the formula would apparently be in the form of I. It'll be like 3i plus 2, or 2 times I squared plus 7, something like that. I is the variable apparently in this particular notation. But it could be x, it could be n, it could be t. The variable could change from problem to problem. But in this notation, we apparently are using i's. So down here then, when it says I equals 1, this is the first input. So according to this notation, the first input will be 1. So that just means if the first input is 1, then A1 is going to be the first term of this series. And then this number on the top is your last input. In other words, A sub n is going to be the last term in this series. So you can imagine different scenarios. In this particular scenario, apparently you're going to plug in 1 first into this formula, and then the part that's kind of assumed, doesn't really say, but you have to assume, is that if 1 is the first input, then 2 would be the second input, 3 would be the third input, 4 is the fourth input, and you keep plugging numbers in until you get to this number. So if this number were, say, 5, well, then you'd be plugging in 1, 2, 3, 4, and then 5 would be your last one. If this number was 10, well, you'd plug in 1, 2, 3, 4, 5, 6, until you got to the 10th input. So that's the way this will roll. You'll see this as we do problems. And just a note, this does not always have to start at 1. That's a pretty typical and logical place to start, but you'll see some sigma notations that start at 2 or start at 10. And that could just be because the problem is a problem that starts at 2 or starts at 10. It just doesn't happen to start at 1 or 0. So there is some flexibility to start with any input that would be reasonable to the problem you're doing. So, for example, let's see if we can turn this into an exercise. We have a story here. We want to add up the first 20 positive odd numbers. So this does seem to be a problem where you're going to be summing. This is a series. So this is a good time to use the sigma notation. And so one of the things I would suggest is always write out a few of the terms. It says 20 positive odd numbers. Well, positive odds would start at 1 and then 3 and then 5 and then 7. And so even if you just write a few out, that just helps you get a bearing or a familiarity with the problem. So clearly you can see a couple things right away. The first term is 1. That's important. And you can see the common difference is 2. That's important. And therefore, remember what goes here off to the side of sigma. That's the formula for the nth term. So if you write out a first few terms, you notice that's arithmetic. It's plus 2 plus 2 plus 2. And if it's arithmetic, we have a formula. A sub 1 plus n minus 1 times the common difference. There's our formula for the nth term. If you do a little simplifying, then it turns into something a little bit smaller. But there's our formula right there. Using a formula from section 11.1, we have simplified the nth term formula to simply be 2n minus 1. We know that is the formula that's going to generate this arithmetic sequence. All right, except I noticed that the notation that we were given was to use I. So I'm going to back up and write this actually as 2I minus 1, not to be confused with the square root of negative 1. This is a different use of the letter I. It's just a counter. And so we're going to use I's instead of N's for this problem. We'll just adjust that. And now that we have the formula, we already know what the first input is, and we can check that. Let's just make sure that's true. If you plug in 1, 2 times 1 minus 1 does in fact give you 1. So this formula is working for the first term. And clearly they told us they wanted 20 terms. So our last n would be 20, or I guess I should say the last I. The last input would be 20. Let's just check that to be sure if that makes sense. If we plugged in 20 here, 2 times 20 would be 40, minus 1 is 39, and that would make sense. 39 would be the 40th odd positive number. If you're not sure, you can count it out there. But there it is. That would be the answer. And that's just the notation. Now we want to find the actual sum. So to find the sum, we could use Gauss's formula. We could take 1/2 of n. There's going to be 20 numbers. And we could take it times the first term, which we could see is 1, plus the last term. The last term is found by plugging in the last input, which we did just to check, and we got 39 as our last term. So now if we type that into our calculator, or maybe just do this in our heads, 1/2 of 20 is 10, 1 plus 39 is 40, so 10 times 40 would be 400. So that should be our sum for the first 20 positive odd numbers. So be watchful of the directions. We did have to find the sum after we got the sigma notation. All right, so that's all I'm really going to do. I'm going to have you read and complete example 6 on page 685, and then there's an extension to that example on 485 and 486, and make sure you complete your notes and do the rest of the assignment as was communicated to you.